This is Dr. S.P. Harsa from Mechanical and Engineering Department, IIT Roorkee. I'm going to present today as a lecture 4 of the topic of this, the strength of materials. In that, you see, we are going to discuss about more of, the stress components that which we have discussed in the previous cases, in the previous lectures, that we found that if you want to describe the general state of stress in which you see there are total 9 number of components were there, including the 3 normal stress component and the 6 shear stress components. So if we have a regular structures like unit cube or parallel pipe, then it's pretty easy to analyze those things, because you see the 3 stresses are there like sigma xx, sigma yy, sigma zz, and then you see we have the 6 different components like tau xy, tau yz, tau xz, and the 3 remaining components. Mean to say that you see if we want to describe the stress for an object or a component, then we need at least the 9 component. That's why you see we found that we need the tensor stress to describe the stress for a point. So you see this part which we have discussed. So in this lecture, the basic thing is that if we don't have that kind of the structure, means if we have any radial structure in which even we discussed that the Cartesian coordinates were there or the cylindrical coordinates are there. But if you are talking about a radial structure in which you see if you are taking any point q, or you see the points are there in that, if you want to check the stress components, then how we can? Or if we have an oblique plane, means that if we cut the sections not exactly perpendicular to x axis, perpendicular to y axis, or perpendicular to z axis, where you see we define the stresses, if it is not there, then what is the stress and how we can relate that stress to the main stress like sigma x or tau yx or tau xy or all those components. So this kind of the information which we are going to dig, digging from this chapter. So first of all, we are starting from the analysis of stresses, in which this diagram has shown. In this diagram you see this we have the component, any machine component which you see on over which these forces are there. So these arrows are showing that where the force application is there, and as we discussed that the force is always defined by the point of application. So you see here these are the point of application where the forces are acting, and this is the Q. Q is the origin, you see or we can say that this is the point where we just want to check it out that what the stress components are there due to these the forces, and you see the stresses are nothing but the intensity of the resistive forces. So how the stress distribution is there all across this domain. So this is our domain, which is neither parallel or perpendicular to x, y or z axis respectively. So consider a point Q in some sort of the structural member, this as shown in this figure. Assuming that at a point we have a Q in which a plane the state of stress exists, that means you see now we are going to consider all those stress components which are existing at this particular state. So the state of stress is described by the parameters sigma x, sigma y and tau xy if we are considering the stresses in x as well as the y component. So this is the one the figure which we want to analyze those things. So if we go again back to the concepts, then we found that this, if you are talking about the xy plane, then what kind of stress distribution are there? So these 3 stress components sigma x, sigma y and tau xy are the dominating stresses, and these stresses are always distributing all across the the structure if we are considering the xy plane. So this diagram gives you a clear-cut picture that actually if we have this xy plane where you see this y and x is there, so this diagram shows you. So in this particular the picture, we can easily describes that we have sigma x all along this x axis. Okay, so this is sigma x, which is of the nature of the tensile stresses, and we have the sigma y which is also of the tensile stresses, and that is why you see we are considering that this is a positive stress. And remaining part you see tau xy or tau yx, we are considering here that this is the tau xy you see here, which tries to rotate this object in a clockwise direction. So we need, if we want to maintain the equilibrium of this object, then we need the complementary stresses. So they are coming from this domain. So this is in this direction and these directions. These two, these directions shows that the stresses are there, the shear stresses are there, tau yx, and they are always exactly equal and opposite to these stress component, and that's why you see we can maintain the equilibrium within these objects. And that's why you see, if you want to consider that, you see the stresses are being formed because of the force application, and if under these stresses or under the force application, if this object is well maintained, like the equilibrium position, it is only possible when all the summation of forces in x direction, y direction as well as the z direction is 0. Similarly, if we consider that, okay, if we have an origin point O, let us say here, and if we are taking moment about this point O either by this shear stress or by this shear stress or by this shear stress or by this shear stress, then we can say that, yeah, from all the 4 components of the shear stresses, whatever the moments are there about this point O, they must be equals to 0. If we consider those things, then we can say that, yeah, this is well maintained, well equilibrium structure under the action of these forces under these 3 stress components. So this is a common way to, common way of representing the stresses for xy plane component, because you see, if we are considering the 3 dimensional, then we need to consider, as I told you, that we need to consider all 9 components, the triaxial form of these, in which all 3 axes are mutually perpendicular. But here only we are considering the 2 axes x and y, where these 3 stresses are there because of the symmetricity of the object. We can say that it's pretty easy to describe all the state of stress by with the using of these stresses. So it must be realized that the material is unaware of what we have called the x and y axis. So whatever the material is there, irrespective of whether it's a like the this stainless steel, high carbon steel, high speed steel, or any ductile material, it is irrespective of that what the stresses are there. If we are saying that it's a ductile material or it's a brittle material, like you see the cast iron or any harder material, we can say that these are the stresses which are always being formed if it is representing of this nature. Means, you see, if you are apply those, you see, like the stresses, like the normal stress component, or we are saying that the shear stress component, then they must be there within those objects. They are well settled within those objects if these forces are there, respective of what the material is. So material is unaware about all those kind of these axes. The material has to resist the loads, respective of less of how we wish to like give the name, or we can say whether they are horizontal, vertical, or otherwise like we can say the material will even fail when the stresses exceed beyond a permissible value. So material provide the resistance based on how much hardness is there, how much stiffness is there. So it depends on, you see, that what is the limit of the loads are there, or what is the limit of the stresses are there, the normal stress or the shear stress. So this is the key feature, this is the inherent property of the material, but it is irrespective of whether it's going in x direction, y direction, or z direction. So this is a real important phenomena about the stresses, that actually though the stresses, either the normal stress or the shear stress in any of the direction, they are the function of the material, but the axes are not, you see, the absolutely depends on that what material is. So you see here, if we are talking about any ductile material, then we have to be very careful that actually what is the stress limits are. So once you see, you define the material, absolutely you see the stress levels are coming, that okay, we can go, like you see, if we have the normal mild steel, then we are always using, you see, 220 megapascal. That means, you see, this is the limiting value. Under that, you see, if whether we can go for the elastic deformation, and if we are going beyond that, then we can say we are going for the plastic deformation, and that you see, like for those limits we can define by the modulus of elasticity and other moduluses. So there are, you see, lot many coefficients are there based on which material you are using, but the stresses are absolutely the function of this material, but the material is the whatever the this is normal stress and shear stresses along these axes, they are not the function of the material itself. Thus, you see the fundamental problem in any of the engineering design, because we are using all this kind of material and the different kind of loadings are there in that. So this fundamental problem in the engineering design is to determine the maximum normal stress and the maximum shear stress and at any particular point in a body. That means, you see, we do not know that actually, you see, if we are applying the load and somewhere you see the shear stresses are maximum, normal stresses are not maximum, whether this material will sustain or it will fail. So we have to be very careful, or we need to design that component whether this can sustain under these values of the stresses or under these types of stresses or not. So the first aim in any of the component design is to know that whether what is the maximum stress and at what point these stresses are exerting or this like executing within those object. And there is no reason to believe appropriately that sigma x or sigma y or tau xy are the maximum value. You see, it is not that actually they are somewhat, you see, they have some value, because if you are talking about sigma x or sigma y, they are simply, you see, the normal stress components. So irrespective of whether we are pulling or compression, they are simply the tensile or compressive forces divided by the effective area. But if you are talking about the tau xy, even it is, you see, like this is nothing but the as per the plane, like tau xy is there. So if we are considering this tau this x and y plane, so these forces are parallel to the axis, but they are not having the maximum value. So you see, we need to be, like chosen the maximum value out of which, so rather the maximum stresses may associate themselves with the other planes located at q. Thus it becomes imperative to determine the values of sigma q as well as tau q. So you see, once we know that, okay, now here in this particular object or whatever the component, we have a point where the maximum stresses can occur due to the variety of loading, then our main focus is to calculate that actually which stress is maximum first and what is the value or what is the limiting value. Based on that, you see, like we can design the factor of safety, and we can we just decide the factor of safety, and corresponding designs are there of the component. So the conclusion of whole discussion says that actually though stresses is one point to calculate within the structure, but the distribution stresses are very important, and we must know that what is the location of the maximum and the minimum stresses are there, the normal stresses as well as the shear stresses, so that we can appropriately design the engineering component which are under the influence of various forces. So here you see, now if you are talking about the shear stress, because we just want to know that actually where the shear stresses are there, and if we have a normal plane, then whether this plane can sustain under the maximum or minimum shear stresses or not. So here you see, like this plane says that actually the force P, if you are talking about these, so these are, you see, the parallel, like the planes are there, and this force P is exerting in this direction, and we have a datum over which, you see, there is a force which is going towards this direction. So if we see the nature of force, then we found that these forces are the parallel forces along this plane. So we have, there is a plane, or we can say the central axis Lm of this object, and whatever the forces are applying here, they are simply parallel to these things, and that is why we can say that whatever the stresses which are inducing due to the application of these forces, they are the shear stresses, and they are very much, we can say well established things are there within this region. So we must know that actually at which region within this object the shear stresses are maximum, so that we can easily design those components by taking the different value of the factor of safety. Okay, so if the applied load P consists of the two equal and opposite parallel forces, as we discussed in the previous case, not in the same line, because if the same line is there, then definitely it is the axial force, we can say, and these are due to these forces we have the normal stresses. But here, as we found that though they are the parallel and opposite forces, but they are not exactly on the same axis, so we have the shear stresses. Then there is like the tendency for one part of the body or another part to slide over the another, and that is why you see the shearing is there, or shear from the other part across any section Lm. So obviously you see, this is the great tendency of the shear stresses, that actually they are always making the shear plane all amongst the center line, or we can say the neutral axis. And neutral axis is always, you see, the axis where this centroid is existing, or we can say where all layers are to be well settled or be well equilibrium within this object. So as we discussed about the shear stresses, they are always set up in the object in the parallel planes. So because of these, like the loads, we found that the shear stresses are there, and they have a tendency to make the shear across this section, and that section we are telling in this particular figure is Lm section. If the cross section at this section Lm, like measured parallel to the load which is A, then we can say that the average value of shear stress is the load application, which is, you see, the inducing the shear stresses divided by A, or we can say P is nothing but the shear force or shear load. The shear stress, like is a tangential to the area over which it acts. So this is the great, the meaning of the shear stresses, because as we have seen that actually as far as the normal stress component is concerned, they are, you see, always act parallel to this surface, the area of matter concerned. But here you see whatever the area which we are concerning, or which these stresses are being set up, or these loads are there, these are always, you see, the tangential to the whatever the these stresses are coming, they are always tangential to the area of concern. So which we need to be very careful that actually once we are just, if we want to find out that where is the maximum stresses, what is the minimum stresses are there, then we have to be very careful that actually what is the area under which these tangential like forces or the stresses are coming within those objects. So if the shear stress varies from point to point, as you see, like we discussed in the previous lectures, that actually if we have irregular geometry where the forces are acting but the forces are not uniformly distributed, because the different forces are there, like if you have a structure at some point, you see some 10, 20, 30 newtons are there, at some point it is a 50 Newton is there, and it is of different nature. Some forces are of tensile nature, some forces are having the compressive nature. If this kind of like the structure is there, and if we want to find it out, the shear stresses of like within this structure, then as I told you that actually we need to discretize the domain into the different segments of the forces, and then once we know that okay, now these are the like for if we have some 7, 10 segments, what we need to do here, we need to calculate the shear stresses for individual segments like segment 1 to segment 10, and then correspondingly we need to integrate those things. So if we have a well defined regions, then there is no problem, you see, because the uniform like the structure is there and the uniformly distributed forces are there. But if we don't have that kind of structure, then what we need to do, we need to define that actually where is the this area of the area is less or area is more, or where is the stress concentration is there. If you see more stress concentration, then we need to take care of the like by taking more factor of safety, and we need to design accordingly. So if we are defining the shear stresses for those kind of regions where the irregularities are there, how we can define? We just define the limit for individual regions, and we are defining the delta P by delta A for that particular regions, and then sum up to get the final value of the shear stress. So this is one meaning. But you see, like if we are discussing about the general shear stresses, then we found that always there is a tendency of the shear stress to move the object in one of the direction. But if we want to maintain, as we discussed in the previous section only, that actually if we want to maintain the equilibrium of an object, then we always need an equal and opposite stresses, and those stresses are known as the complementary stresses. So if you see this figure, then we have this figure, you see, on like the plane AB or CD, there is a stress component on this, and this stress component, if we are denoting by sigma this tau, then these things are there, and these like the dash is showing that the shear plane is this is my shear plane or which these stresses are occurring. So if I am saying that if I have a ABCD, which is a a rectangular element which has like the side of x, y, z, all these three mutually perpendicular sides to the plane of like the paper, then we can say that the shear is like shear stresses are existing at this AB as well as the CD plane. Okay, so now you see if we exactly like figure out this particular problem, then we found that this shear stress is always tries to tend this object towards the clockwise direction. You see here like this shear stress always influencing this segment of element just go towards this direction, while this one is also just tries to like tending this element towards this direction, this CD portion. So that means you see like if we combine both the effect, then we like we observe that there is a tendency of this element under the influence of this shear stress which is moving towards the clockwise directions. So but if we want to maintain the equilibrium side, then we need the equal and opposite at these two faces, like at AD and CB, which is exactly equal and opposite to the applied stresses, applied shear stress sigma. So here you see it is obvious that these stresses will form a couple, as I told you that, and the couple magnitude is this tau into xz, that is the force, into y. So that is the couple. So tau into xz will the force exerting at xz plane into the y distance, which will give you the couple always try to tend towards the clockwise direction, which can only be balanced by tangential forces on the plane, as I told you in the AD and BC, these two parallel sides, and these are known as the complementary stresses, or we can say the existence of shear stresses on the sides of AB and CD of the element implies that the shear must be also if the shear stresses are there, there must be counterbalance shear stresses, and those counterbalance shear stresses are known as the complementary shear stresses on the other side of the element to maintain the equilibrium. So this is, you see, the one form of the shear stresses. So if I am saying that the sigma is the shear stress, then sigma dash is the complementary shear stresses, and if the sigma dash be the complementary shear stresses inducing on the plane AD and BC, then we can easily maintain the equilibrium by taking moment by, you see, if we have on the one side of this sigma into xz. So if the xz is the plane, and if we multiply, so sigma into xz is the force, and if we multiply by y, then we have the total moment, which is exactly equal and opposite to the couple which is coming due to the complementary shear stress. So it is the sigma dash, which is complementary shear stress, into yz. So that is now the total force in the yz plane into distance in x. So now you see, if you compare both the things, then you will find that sigma equals to sigma dash. Thus every shear stress is accompanied by equal complementary shear stresses. So you see, we need a balanced part opposite, which is equal and opposite to the shear stresses, if we want to maintain the equilibrium of any component. Okay. So you see, shear stresses and complementary shear stresses are, you see, the two forms of a coin, which is always there to maintain the equilibrium of a object. Then you see, like till now whatever we have discussed, we were discussing about like the regular geometry. At the end, you see, we have the force application. Because of the force application, we have the stresses, shear stress, normal stress component. Even in the shear stresses, different shear stresses are there, the different outer surface of those things by taking the oblique planes and by taking the normal planes and all. But if you want to calculate that, you see, inside those things, that means if you want to check that what is exactly happening within, like at different points in the object by under the application of forces, then you see, we need to check it out the stresses on the oblique plane. That means, you see, we need to cut the plane at a theta angle, which is not essential that it has to pass through from the center of the origin, or we can say the center of mass of this object. It can pass from the initial part or the lower part or any part of that. And if we cut that plane, and if we want to check it out that what the stresses are there, the normal stress component, shear stress component, that all the kind of information which we are going to discuss under the heading of stresses on the oblique plane. So till now, you see, we have like deal with either the pure normal direct stress or pure shear stress. In many of the instances, however, both direct and shear stresses acts, and the resultant stresses across any section will be neither normal nor tangential to any plane. That means, this is the realistic situation, that actually if you want to check it out that where is the maximum shear stress is there, where is the maximum normal stress is there, where is the maximum the minimum normal stress or minimum shear stress, then whatever the analysis which we have done in the previous cases, that is not sufficient, or that is not, you see, the perfect to get the all like answers. So what we need to do here, we need, if we want to do the realistic analysis, then always we need to check it out that actually what is there, what the stress levels are there under the oblique plane. So you see here a plane of stress, a plane state of stress in any two dimensional, like the state of stress, in a sense that the stress component in one direction, like all the stress components are there, they are all equals to 0. That means, you see, like till now, you see, if we discussed, if you just focused on that, we discussed that we have the stress tensors in which the 9 components are there, but all 9 components, or we can say 3 by 3 matrix is valid if we have all, like the triaxial state, the state of stress is there, or we have all 3 mutually perpendicular axes. But if you are talking about the 2-dimensional state of stress, that means, you see, the one direction is gone. So if you are saying that if I am considering only x and y, this x direction and the y direction, that means there is no stress, means I am assuming that there is no stress component is there in the this vertical direction, or I should say the z direction. So what has happened, you see, this kind of, like the plane stress, or I should say that actually the 2-dimensional plane stress is always calculating for these 2 directions, and that is why it is known as the plane stress. That means for xy plane, yz plane, or xz plane, that means, you see, one direction is just we are assuming that there is this other direction is not existing. So here you see, if we consider this case, then we found that actually that this is, like the plane stress is there, which is only there in the xy direction. So you see the sigma z or tau yz or tau zx, means either the normal stress component in the z direction or the shear stress component in the z direction, which is coming due to the force in the z direction, like you see here tau yz, means the y is the domain and the z is force, or tau zx, means the z is the domain and this x is the force. That means you see these stresses are not exerting, not existing in the plane stress. Okay, so this is the plane stress which is always there in the 2D plane. So now you see in under the two-dimensional state of stress or plane stress, consider a general case in which we have a bar which is under the influence of the force in the y direction only. So if you see this figure, then you see here we have a two-dimensional object. This is a rectangular bar, and the force is, the tensile pulling is there in the y direction only. So now if you see this thing, then we found that actually these, due to these, you know, like the force component in the y direction, we have a tensile pulling, the tensile forces are there, and due to these tensile forces we have the tensile stresses in the y direction only. So we have the sigma y. So sigma y is nothing but equals to, if you consider this BA is a section, then we found that the sigma y is nothing but equals to the applied force divided by the area. But if we want to check it out, the oblique stresses of the stresses at the oblique plane, then we need to cut the plane at this BC. So this you see now, BA is a normal plane which we have discussed in the previous cases. BC is a oblique plane. If you cut this plane by this section at an angle theta, this so now we want to calculate that actually what the stresses are there of the oblique plane. So we can say these stresses at the oblique plane are sigma theta, that is the normal stress component, tau theta, that is the shear stress component, and they are, you see, exerting or on this oblique plane by these. We can simply denote it by this sigma theta and tau theta. So you see now if we cut this portion, so now we have this oblique plane, and we can simply denote, we can show by, you know, like if we have a unit cube, simply cut that unit cube, and now we have, you know, like these all three directions. So what we have, this is my A, B, C, you see this is AB where this part was there, or which we have the sigma y, and we have this BC of which the plane is cutting. So this is my oblique plane, and this is, you see, the straight line where you see, you know, like we are considering the sigma y or in the y direction. So thickness of this element in the z direction is always thin, because we are considering that there is no element is, you know, like observing under that, and it is taken as the unity. So because you see, you know, like this is the unit cube, so we have to consider, not we need to, we have to consider that there is a unit thickness is there all across these all across this particular this structure. So we have unity means unit depth is there of these kind of things. So if you consider these, you know, like the plane, that if we are, you know, like if you are focusing on the main plane, then we have the sigma y, okay, but if we are considering the oblique plane, then we have the sigma theta, tau theta, and if we resolve these stresses, then we have the theta over this particular part. So now you see, we just want to set up the relationship between the sigma theta and tau theta, that means the stress components at the oblique plane and the stress components at the outer surfaces, that means you see the sigma y. So you see the stress acting at a point is represented by the stress acting on the faces of the element enclosing to the point. That means whatever the, you know, like the faces are there, we have to concern about all those stress components which are there, which are existing all around this plane. So the stresses change with the inclination of the planes passing through that point, that is the stress on a face of the element vary as the angular position of the element changes. So obviously you see, you know, like because as we change the angular position, definitely there is a change in the magnitude is there of the stresses, because if you relate those things, then we found that actually there are two resolution is there of the forces in the x direction and the y direction, and it is always being focused by the cos or the sin theta. So what the exact relation is there, and based on those relations we can easily found that actually if you change the angle, there is, you know, like the difference is there in the magnitude of those stresses. In this figure, you see, you know, like we have seen that the object is under the influence of the tensile forces in the y direction. That means you see the tensile load is there under, you know, like the influence of these stresses. That means we have the tensile stresses in the y direction, and we just want to see that if we cut the plane under the influence of this force, then what the exact relation is there of the, you know, like the sigma theta or tau theta, which are nothing but the stress components at the oblique plane with only sigma y. That means we are only considering there is no stress component is there, only we have this shear component. So now if you are simply, you know, like carefully watching about those things, then we found that there is a unit depth is there under the triangular portion of ABC. So if we resolve the forces perpendicular to BC in the previous case, then we found that we have, you know, like just in the perpendicular part sigma theta into BC, that is the plane, into unit depth, because we are considering the depth is unit, is exactly equal to the sigma y into sine theta, because now you see only the normal force is there, so normal stress component is there in the y direction. So sigma theta BC into 1 exactly matching by sigma y into sine theta of AB, because AB is the plane where the sigma y sine theta is acting towards that into y. So if you resolve those things, then we found that actually AB by BC is nothing but equals to sine theta, or we can replace this AB, which is you see the plane of the y, the perpendicular to the y axis, is nothing but equals to BC sine theta. So from resolving these equations, we found that we have sigma theta BC into 1 is equals to, like if you put those things, then we have sigma y sine theta into BC sine theta into 1, or we have the stress at the normal stress component at the oblique plane is equals to sigma theta is equals to sigma y sine square sine 2 theta, because if you resolve those things, then obviously you see the sine square theta is there. So you can simply like resolve that part, and it is equals to that, or you see like the BC will cancel out. Meaning is pretty simple, that actually we can easily relate the stress component at the oblique plane by whatever the force influencing is there of the object. So again you see this is the normal stress component, then what is the shear stress component, we can again easily calculate by that tau theta into BC in the different domains. So tau theta into BC, which is the cutting plane, into 1 is equals to sigma y cos theta into AB sine theta into 1. So you see like as we discussed in the previous case, that AB by BC is cos theta. So you can simply replace AB equals to this BC cos theta, or tau tau theta BC into 1 will give you sigma y cos theta into BC sine theta into 1, or we can say that it is nothing but the tau theta is equals to half of sigma y sine of 2 theta. So now you see these, either the sigma theta in the previous case you see, which is this tau y sine of 2 theta, or the sine square theta, or we can say this tau theta, which is half of sigma y sine of 2 theta, they are only coming because of the influence of the pure normal stress. There is no shear component is there, but because of the pure this normal forces, we have both the component at the oblique plane, means we have the normal stress component, we have the shear stress component, and what the values are there we can easily get. So this is the beautiful like the meaning of these things are there, that we can get all those values. Though the shear stress we are not, there is no shear forces are there, there is no parallel forces are exerting on the different layers of the structure, but if only the normal stress is there, that means if only pure like the tensile or the compressive forces are there at any of the axis, we have both the component within the structure, like the normal stress component and the shear stress component, the values are these. So you see here again we can resolve these cases by putting the plane at different angles, like if theta is at 90 degree, then whatever the BC, which is the cutting plane, was there will exactly parallel to the AB plane over which the sigma y was exerting. So this we can say that this tau theta, whatever you see, if you put the theta 90, then this is tau theta, okay, which is exactly equals to 0. That means there will be no direct stress, or the normal stress is there, or by examining the equations 1 or 2, whatever you see for the sigma theta and tau theta, we can simply conclude that the value of direct stress sigma theta is maximum, and it is equal to the sigma y when the theta is exactly at 90. Means you see, if you cut the plane, the theta exactly parallel to the BC or exactly parallel to the AB, then we have the exact value whatever the values are exerting at the top of the surface, if you want to compute the this normal stresses at the different layers of the structure. And the second case is there, if the shear stress tau theta has a maximum value which is equals to half of the sigma y at 45. That means you see, if we cut the plane at exactly 45 degree, then whatever the value of the shear stresses are there, these are half of the half of the applied this normal stress. And the third part, if the shear stress sigma theta and or tau theta are not simply like resolution of sigma y, that means you see like if only these other two stress components are not exerting, then we cannot relate the sigma theta or tau theta with the sigma y. That means you see like we have to be very careful that actually there are maximum or minimum values of normal stress and the shear stresses are exerting, even if the shear stresses are not being exerted on the outside of the surface. So, now you see here we have a material which is subjected under the pure shear stress. That means, in the previous case we had discussed about when the normal stress component is there and like the material is subjected by that normal forces, but here you see we are considering one element as you can see here in this figure, that this element is under the influence of the shear forces, and the shear forces are being applied at these two like the sides, which is AB side, this tau xy is there, and the DC side which is tau xy is there. So, here because of these tau xy, now the see the stress distribution is there in this particular like the portion, and we have the another like the as I told you that actually the complementary shear stresses are there, the tau xy, the tau yx, which is exactly equal and opposite to the these shear stresses which are being applied. That means, you see here there is no normal stress component in this structure, only the purely shear stresses are there, the complementary shear stresses are there just to balance those things. And because of that, now we just want to check it out that actually what the stress components, means the normal as well as the shear stress components are there at the oblique plane. So, you see here we simply cut the plane at, you see the PC, this is the cutting plane, the oblique plane I should say, and at the PC you see now we just want to check it out that what the stress components are. So, we have the sigma theta and the tau theta at these PC plane, which is you see the sigma theta in this direction and the tau theta in this direction. So, now you see the complementary shear stresses which I was talking about is exactly equal and opposite like effect is there against that the applied shear stress is on the two different sides of AD and BC, in order to like the prevent the rotation of the element, or we can say we just, if we want to maintain the equilibrium of the element, we have to like put the complementary shear stresses. Since the applied and the shear stresses are equal and opposite, then you see like of the value of xy planes, then you see we can say that the this object is under the equilibrium part. Therefore, you see like both are being represented by the tau xy, because the tau xy and tau yx they are equal and opposite. So, it has the same physical meaning if you want to apply those things. So, now come to like the equilibrium portion of the PBC, where PB is like the applied part is there, and the PC is that part where the cutting or we can say the oblique part is there. So, if you look at closely, then you find that you see we have the sigma theta which is exactly at these point, you see which is coming out from this PBC plane, and we have the tau theta which is exactly, you see, the perpendicular to these things. That means the shear stress is there of this, the normal stress is there, and if you want to check it out the outer surface, that actually what exactly stresses are being set up. So, you can find that you see like these components, the tau xy cos theta and the tau xy sin theta are the resolved like the forces are there if you resolve at the theta angle, because we have the tau xy which is this one, you see like the tau xy is there which is well set up on this plane or on this plane, you see you can see this is tau xy, this is tau xy. So, now if you resolve this, if you resolve in this way, means if we have the tau xy perpendicular to this y axis. So, if you resolve at the theta, you find that this is the tau xy cos theta, this is tau xy sin theta in this direction. So, we have both components tau xy cos theta, tau xy sin theta, just to balance, just to counterbalance the normal stress as well as the shear stress due to the oblique plane. So, now you see if you resolve those things, then you find that assuming the unit depth, again you see we are assuming that whatever the structure which we have, it has the unit depth, and if you want to resolve the like those forces, then we need to see that actually what exactly the forces are there just perpendicular to the this oblique plane PC. So, you see here we have the direction sigma theta which is exactly normal to the plane PC. So, if you consider the PC where the sigma, this is PC, you see this is PC and sigma theta is exactly normal to this plane. So, if you resolve this, then you find that sigma theta into PC into 1 because of the unit depth exactly equals to the tau xy into PB cos theta, which is exactly, you see like equating that part, plus tau xy into BC sin theta. It is the composition of these. Or if you divided these things, then at the end you see what we have, you see like if you just remove those things, then we have particular sigma theta PC equals to tau xy PB cos theta plus tau xy BC sin theta, means that here we have only the application of tau xy, means the only pure shear is there, but because of that you see we have the normal stress component in the oblique plane and we have the shear stress component in the oblique plane. So, now you see like if you resolving these things, as I told you that PB by PC equals to sin theta or BC by PC equals to cos theta. So, if you put those PB and PC value in the previous equation, then you found that sigma theta Pc into 1 at the left hand side is equals to tau xy cos theta into sin theta into Pc, which is equals to Pb, and plus tau xy cos theta into, in place of Bc you can put sin theta Pc. So now you see Pc will cancel out because it is exerting on the both the side. So we have what this is this sigma theta into 1 is equals to tau xy sin theta cos theta plus tau xy cos theta sin theta. So if you sum up, then you found that we have sigma theta equals to tau xy 2 times sin theta cos theta. So at the end we have the sigma theta which is occurs, like which is occurring in these element due to the purely shear stress, tau xy is equals to sigma theta equals to tau xy sine of 2 theta. So this is, you see, the normal stress component, like because of the tau xy, and again you see if you resolve the forces in the perpendicular plane, then you found that the normal stress component is there. But if you found that if the shear stress component is there, like the PC plane is there, and if the parallel forces are there, and due to the parallel forces we have the shear stress component. So if you want to resolve the shear stresses which is at the oblique plane, and if you want to compare both the things with the oblique plane to the main plane, then you found that actually we have this tau xy PC into 1 is equals to tau xy PB sin theta, or we can say, you see, minus tau xy Bc cos theta. The negative sign is coming because you see, the stress, because we want to apply the complementary shear stresses, so that actually whatever the rotation is there we can prevent that rotation, because of the complementary shear stress. So always the negative sign is coming in resolving the shear stresses. So again, converting those various quantities into, the terms of Pc, we found that we have the tau theta, means the shear stress at the theta is equals to minus tau xy cos of 2 theta. So the meaning is that we have normal stress component, we have shear stress component which is coming due to the influence of the shear stress tau xy, and which has the different values of like sigma theta is there, then we have the tau xy sin 2 theta. If the shear stress is there, the tau theta which is equal to minus of tau xy cos of 2 theta. The negative sign means that, as I told you, the sense of the tau theta opposite to the assumed one. So obviously you see, always it comes that actually if you are not concerning about the complementary shear stresses or the negative shear stresses, then you cannot say that whatever the element which you have chosen, it is under the equilibrium position because of the applied stress. So always we need to assume that the applied stresses are there along the parallel axes, but we have, you see, the other side of these, the complementary shear stresses which can balance these stresses. So we can say from the other equations we have sigma theta which is tau xy sine of 2 theta. The equation 1, this one represents that the maximum value of sigma theta is tau xy, obviously this, when the theta is at 45 degree. Means, you see, if you cut the plane at 45 degree, you have, you see, you will find that the maximum normal stress which is exactly equal to the shear stress, applied shear stress, when you cut the plane at the 45 degree. And if you just introducing by considering the equation of this by taking, you see, the tau theta equals to minus tau x cos of 2 theta, if you put that particular thing, then you found that actually the tau theta is exactly equals to 0. That means it indicates that the maximum value of tau theta is tau xy when theta is exactly 0 or 90 degree. That means, you see, if whatever the PC plane which we have chosen, if it is at just perpendicular 90 degree, or if it is, that means if it is exactly at the PB, or if it is perpendicular to AB, that means just this parallel part is there, then we have the maximum value of shear stress that is equal to the applied shear stress tau xy. But if it is, you see, if we are cutting those planes at 45 degree, then only normal stress component is exerting, that is sigma theta. There is no shear stress portion is there at the 45 degree of angle. From the equations all, you see, either sigma theta in the one equation or tau theta equation 2, we can easily calculate the maximum or minimum values of the normal as well as the shear stress component. So from equation 1, it may be noted that the normal component sigma theta has maximum or minimum value of plus tau xy if the tension is there, you see, if the tensile forces are there, minus tau xy if the compressive forces are there on a plane where, you see plus minus 45 degree of angle of rotation is there. That means you see if you cut the plane at 45 degree of angle, whatever the planes are there of these two planes, if I say that at these planes the normal stresses are always maximum, the sigma theta, which is equal to the applied shear stresses. And these planes are tangential. Like if you want to check it out, the the shear stresses at the tangential plane, that means you see 0 or 90, then you will find that the shear stress component has the maximum value. And if you want to check it out, the like at these plane where these sigma theta is maximum, means the 45 degree, the tangential plane where the shear stress component is 0. So you see you can like vary all those things. You can check the minimum as well as the maximum values of sigma theta or tau theta corresponding to the different planes. Hence the system of pure stress which we discussed recently, you see here, produce an equivalent like direct stress system, one set of the compressive and the one set of the tensile each located at the 45 degree to the original these directions as depicted to the figure. So if you see this figure, you see we have like this component which is influencing by only shear stresses. You see these shear stresses are there. Now if I rotate at 45 degrees, so you see now this is the rotated plane which is exactly at the 45 degree. So what we have only, you see, at the 45 degree of angle, only these stresses are absolutely converted into the normal stresses. That means you see here these stresses are being applied, the shear stresses, counter shear stresses are there, but at the end you see if you rotate this element, simply by rotating this element, all the shear stresses are being exactly converted to the normal stresses. Or we can say, if you come down to these things, you see we have this element which is under the influence of the shear stresses, and if you compute those things, then you find that you see at these planes where the 45 degree planes are there, this one sigma is like sigma theta I should say is tau xy, or sigma which is sigma theta also is minus tau xy. So we have both the these stresses are there, but the shear stress, pure shear stress, will give you only the normal stress component at the 45 degree of angle. Now you see here this third case, the previous two cases which we discussed, when the material is under the influence of pure stress and when the material is under influence of pure shear stress. Now when material is subjected by two mutually perpendicular direct stresses, means you see we have direct stresses, but both are mutually perpendicular, like the x direction or the y direction, and they are acting in the tangential direction. So now you see, consider a rectangular element which is being shown here in this diagram of unit depth. So again you see we are considering of the unit depth subjected to a system of two direct stresses, both are tensile as I told you on the right angles of each other. That means both are mutually perpendicular. So if you see that, then you will find that the sigma x is there on these two like sides of the rectangular element, sigma y, again you see we have like these two these tensile stresses are there in the y direction. So now you see if you want to check it out, because of the influence of these two mutually perpendicular stresses x and y, what is the like the stresses at the oblique plane, again cut the plane here by this AC, and we just want to check it out that actually what is the value of the sigma theta and tau theta is there at that. So cut the plane, and we have now you see the two different like regions. At one region now we just want to check it out at AC, the sigma theta and tau theta is there, but other two plane, this is one, we have sigma sigma x. So how we can resolve these things, like sigma x cos theta, sigma x sin theta, or here sigma y cos theta, which will come here, means sigma y sin theta and sigma x cos theta in the other direction. So now you see we just want to resolve these stress components as per the value of these sigma theta and tau theta with the sigma x and sigma y. So only shear stress is there, there is no only pure this normal stress is there, there is no shear stress component. So now you see within the equilibrium portion of the triangular part ABC, if we want to resolve these forces, then we have first sigma theta is into AC. So AC is, you see, the inclined part. So sigma theta into AC into unit depth, that is 1, is equals to sigma y sin theta into AB, where this AB is acting, into 1, plus sigma x, which is, you see, cos theta into BC into 1. So now you see converting this this AB and BC in terms of AC, so that AC cancel out from this side. So we can simply like resolve those forces. We have sigma theta is equal to sigma y sin square theta, because AB by AC is sin theta, BC by AC is cos theta, so plus sigma x cos square theta, or further we can say that the cos square theta minus sin square theta is cos 2 theta, or we can say it is 1 minus cos of 2 theta by 2 is nothing but equals to sin square theta. So if you do this kind of manipulation, then we found that at the end that we have sigma theta is equals to 1 by 2 sigma y cos of 2 theta plus 1 by 2 sigma x cos of 2 theta, or by rearranging those things we have the sigma theta because of the two mutually perpendicular stresses sigma x and sigma y. We have the final the stress at the oblique plane in the normal direction sigma theta is equals to sigma x plus sigma y by 2, which is not influenced by any theta. See this is a constant quantity. So here, so this is one constant quantity and one is influenced by the theta. So 1 sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos of 2 theta. So we can resolve these things, that actually what is the value of the maximum or minimum sigma theta is there if we have the different angles, like if you are cutting the plane at theta equals to 0, 90, 45 or what like that. So you can get those values. So now you see, resolving these parallel to AC, then we have sigma theta AC into 1 is equals to minus tau of that, because now you see we just want to check it out the other component which is parallel to AC, that means the shear component is there. So minus tau xy cos of q into AB into 1, which is due to that tau xy in vertical direction AB, or we can say tau xy BC into sin of theta into 1. The negative sign appears always, you see, because of the complementary series stresses. Okay. So to balance those component. So again you see, converting those all variety of the components, we found that actually what exactly the value of tau theta is. So if we resolve those things by equating the segment into the x as well as the y direction, we have tau theta into AC into 1 is equals to this tau x. In this particular figure we can find out the tau x into cos of theta into sin theta minus sigma y sin theta cos theta multiplied by AC. So we can find it out that the tau theta is nothing but equal to sigma x minus sigma y into sin theta cos theta, or you can convert into 2 theta parts. So we have sigma x minus sigma y by sin of 2 theta. So we have the final value of tau theta which is equals to sigma x minus sigma y into sin of 2 theta. So now you see, by by applying the two different forces at mutually perpendicular axes, we can also get the sigma theta or tau theta at the oblique plane by measuring those values by sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos theta, which will give you sigma theta. Sigma x minus sigma y by 2 into sin 2 theta will give you the tau theta value. The conclusion of this whole discussion says that the following this conclusion which we can draw that the maximum direct stress can come because by applying theta equals to 0 or 90 degree, which is equals to exactly the sigma x plus sigma y by 2. That means you see, if the mutually perpendicular stresses are there, the maximum direct stress will be of sigma x plus sigma y by 2, which is equal to which is coming when the theta is equals to 0 or 90 degree. Maximum shear stress is coming on the plane where the plane is applied, you see, at the 45 degree. Means you see here, now the things are changing. Two mutually perpendicular axes are there, stresses are there, and under the influence of these stresses we have the maximum value of shear stress at an angle of 45 degree, which is equals to sigma x minus sigma y by 2. So we have the maximum value of direct stress as well as the maximum value of shear stress at the oblique plane if we apply these things. So now in this all discussion we discussed that actually you see if the pure shear stress, pure normal stress is there, pure shear stress is there, or two mutually perpendicular pure normal stress is there, then how we can get the stresses at the oblique plane irrespective of whether it is a sigma theta or tau theta. So in this lecture you see you found that actually we have to be very careful that what is the value of the maximum and the minimum stresses are there, normal as well as the shear stress. So in the next lecture we are going to discuss that actually what has happened if the two mutually perpendicular axes are there and it is being influenced by not only the normal stress but the combination of the shear stress. Means you see, now we have the combined forces, perpendicular as well as the parallel forces, then how we can resolve the normal stress and the shear stress component to the both you see at the oblique plane as well as the reference plane. Thank you.
Thank you.